In this session, we'll be talking about the sampling distribution, wherein first of all we'll try to understand what are sampling distributions, how are they really different from the distributions associated with the raw data, right? So what are we typically calling as sampling distribution of the mean, sampling distribution of the variance? So sampling distribution of specific statistics that are typically computed on the sample. So within that context, we also need to understand some key terminology relating to the population versus the sample, right? How do we differentiate them, and what are the terminologies that are specific to population, what are the terminologies that are specific to the sample. Then we will introduce you to one of the most important theorems in statistics, one of the probably I can say the heart of a large number of statistical inferences that we are making. One of the major contribution to that is the central limit theorem. That is the base for various statistical analysis that we are performing. So we will be discussing something about the central limit theorem. Then we will also talk about a couple of distributions which are based on the central limit theorem and which are very appropriate when we talk about the sampling distribution, right? So we will be talking about the chi-square distribution, the T distribution, F distribution, which are very important when we are talking about the sampling distribution. Because the sampling distribution of the mean, we will bring in the T distribution, and if I am talking about the sampling distributions of the variances, we would be talking about the chi-square distribution as well as the F distribution. So let's try to understand what each of these distributions are, how do we really understand them and interpret them. So we will get started. As an introductory part, let's understand when we talk about statistics per se, right? When we are talking about statistics, so the first layer of statistics, which we typically call as the descriptive statistics, which is all about reporting the existing data, right? So we talk about creating some kind of tables, creating some kind of charts, graphs, etc. So we are trying to report the existing data and try to see what has happened. So it's more of historically what has happened. So it is a reporting of the past. That is the descriptive statistics. But the other major world of statistics, which is what we are calling as inferential statistics, that is the core, the core part of the statistics, wherein we are making conclusions regarding the data and using the historical data to make some kind of prediction. So these are the two major activities that we are going to perform when we are excelling in statistics. Either I use statistics to make conclusions regarding my data, or I would like to make predictions based on the data that I have chosen to build a predictive model. So we do these things in a carefully planned experiment, because we are not collecting the whole data here, right? We are collecting only a part of the data, because in many cases it's very difficult to collect the entire data also. So we will try to collect only a part of the data, which is what we call as a sample. Use that sample, and along with that sample we use a bunch of statistical techniques to really make some kind of conclusions or even predictions regarding the whole population. So we are taking a sample using a bunch of statistical techniques. We are doing a conclusion or a prediction for the entire population. So if I had taken the whole data of the population, I don't need to go with this process. But many cases it's very difficult to gather the data of the entire population. So that is where we say the conclusions and predictions resulting from chance outcomes, right? Because there is some amount of randomness that is there because we are taking only a subset of the data. But that randomness we are trying to reduce by carefully planning the experiments and investigations. So that is what, if you want me to define statistics in one single line, that is how I typically define it. So we are taking a sample observations, looking at the overall task of statistics. We are taking sample observations from a given population, and whatever we compute on the sample, right? We have taken a few data points, which is a subset of the whole population. We use the results of the sample. Probably we may compute the mean of the sample, we may compute the variance of the sample. So we do some kind of computations on the sample. Whatever the computations that I make, I use those results to make inferences about the population. So I will make inferences about the mean of the population, variance of the population based on that particular value computed for the sample plus some kind of statistical techniques that are added along with it. So that is what we do as a part of the entire statistical analysis, right? When we are defining the whole statistical analysis, this is what is the scope of our activity, right? Then here in this context, we are now introducing a few definitions. Statistic. So when we are talking about computation of few functions on the random variable, especially with that of the sample. So if I am computing the mean of the sample, it is called as a statistic, denoted as x bar. If I am computing the variance of a sample, I'll call it as S squared, but this is again a statistic. Whereas the same thing, if I'm computing the mean of a population, the population mean, I denote it with mu. Similarly, the population variance, I denote it with sigma squared. Standard deviation of the sample is S, whereas for the population it is sigma. So what we typically see is the notation is also different. For the statistic, whatever you are computing for the population, these things are called as parameters. The same computations which are applicable to the sample, they are called statistics. So all these are typically the statistics associated with the sample. The properties of these distributions, based on these values, I will be able to make probability statements regarding the inferences from the sample to the population. I'll make inferences about the population by looking at the sample, going with this kind of a mechanism. And when we have to define the process called statistical inference, we are drawing conclusions from the sample about the population from which it is drawn. So I am using a sample. Using that sample, I am trying to make some kind of inference regarding the population. I am using the results of the sample to make some kind of inferences regarding the population. That is what, in a nutshell, what we are looking at when we are calling statistical inferential process. Now, before we get into the core of the sampling and the sampling distributions, a few important terms. Population I have already defined, a set of numbers from which the sample is drawn. And the distribution of that numbers associated with the population is what we call as the population distribution. But if we are taking some subset of that population, that is what we are calling as a sample. And if I am looking at the distribution of that numbers that constitute the sample, that is typically called as the sampling distribution. Now, many a times when we are creating the samples generally have to be a good representatives of the population. To a large extent, when I am taking a sample, the sample should be a good representative of the population. Then only I will be able to generalize whatever the computation that I am making on a sample to a population. But many a times we see that the samples, they are not that representative enough where I can create valid generalizations about the population. Now this is where some kind of techniques come into picture. On one side we say the sample should be random. So I'm not explicitly choosing some kind of values out of the population and say this is the sample. To a large extent the sample should be as much random as possible. Now this is where we say if x1, x2, xn, they are all IIDs, independent and identically distributed random variable. So they are independent of each other. Selection of 1 does not influence the selection of 2. Selection or non-selection of 2, that is independent. Identically distributed. All the data points that of the population will carry one single distribution itself. It could be normal, it could be binomial, whatever it is, but the whole data is coming from one single distribution itself. So if x1, x2, xn are independent and identically distributed random variables, then I say they can be a part of the random sample. Now I can say x1, x2, xn, they are a random sample from an infinite population based on the distribution that we are talking of. So I can very well, when they are IIDs, I can pull up the values associated with each of these and say that that could be a random sample. So in general, in the real world, we pull out the random samples from the population which are finite, but they should be large enough. The population should be so large that literally I can treat it as infinite, even though it is countably finite. So from those kind of populations, it's very, very difficult to bring the overall population and do computation based on the overall population. We still resort to the concept of sampling. So statistical inferences, whatever we are making, whether it is inferences regarding the mean, the more common inferences that we generally make, we make inferences regarding the mean of the population. We make inferences regarding the variance of the population. We make inferences regarding the proportions of the various categories in the population. So whatever are the inferences that we are going to make, first thing is we compute the statistics of those based on the samples. Like I will compute the sample mean. So I will take the sample data, sum them up, divide by n, computing the sample mean. Or x minus x bar the whole squared summation by n minus 1 is nothing but the sample variance. So I will compute these things based on the sample mean, sample variance. I can very well compute based on the sample data that I have pulled out. And remember, the sample mean, sample variance, whatever are the computations that I am performing on the sample, they play a very important role in determining the parameters of the population. So when I am doing a sample mean, this plays a very important role in the estimation of the population mean. Computing sample variance, this plays an important role in the estimation of the population variance. So that's one of the reasons pulling out a right sample, making the right set of computations on the sample, all these things become more and more important for us, right? Then we'll move on to the next concept in this regard, where we are talking about the sampling distribution of the mean. Now, let's say I have taken my population size is too huge, and I have considered a sample of size 100 from that particular population, and I am computing the mean of that particular sample. So it could be some x1. If this sample changes, the same 100, now again I pull a different 100 from the same sample, the mean could be something else, x2. Similarly, if I pull out some other 100, it could be x3, which means the statistic that I am computing, it will change from sample to sample. Though the sample size is 100, if I am pulling one type of sample out of the, let's say my population is close to a million. Out of this million, I am pulling 100 randomly and I am computing the mean of that 100, which would be x1. Again, I am pulling another 100, computing the mean, which could be x2. Now, there is no guarantee that x1 needs to be same as x2. x1 and x2 can be very well different. So that is what I meant. Sample statistics that I am computing, they can vary from sample to sample. So which means the sample statistic also follows a distribution. There is a distribution that is associated with the sample statistics as well. And that distribution is what we are calling as sampling distribution. Right? So whatever is the sample statistic, whether it could be sample mean or sample variance or whatever, that particular sample statistic, I am looking at the distribution of the sample statistic. That is what we are calling as the sampling distribution. So if I say x1, x2, xn, they are a random sample, and let's assume the population is having a mean mu, right? The population from which this particular sample is being drawn. Let's say the population is having a mean of mu and variance of sigma squared. Then we are simply saying the expected value of the sample mean. Expected value of the sample mean is mu and variance of the sample mean is sigma squared by n. This is a very, very important concept that goes into the central limit theorem as well. One of the most important fundamentals which we have to understand. So if I am talking about a population which is having a mean of mu and variance of sigma squared, I am trying to pull a random sample of size n from that particular population, right? We get different combinations of samples. Now what we are saying is, if I take the mean of the sample mean, expected value of the sample mean, it should be equal to the population mean mu. And if I am looking at the variance of the sample mean, it should be equal to the variance of the population divided by n. So if you can, if we have to quickly look at how this works out, let's set some y equal to x bar, right? We have to find out x bar. So we will set, we will take y equal to x bar and ai, let me take it as 1 by n. Now based on this, if I am saying expected value of x bar, it's nothing but I am integrating, I am summing it over 1 to n, 1 by n times expected value of x, which is nothing but mu, which is nothing but n times, because I am doing 1 by n times 1 by n of mu, 1 by n of mu, which is becoming mu. So we can very well, because expected value of xi, each one, the expected value of it should be equal to mu. Then because I am having expected value of x bar, I am taking it as 1 by n times mu, and that I am adding it over all the values of n, which is finally giving out mu, which is what is the result that we are getting. So if the random variables are very much independent, and now if I am taking y is 1 to n ai xi, right? Let me take y as ai xi. Now what is the variance of y? We have already talked about. Variance of y would be nothing but the constant would be squared. ai squared times variance of xi. So I will be getting ai squared times variance of xi. And now I want y is nothing but I have called it as x bar. So that is where I will compute variance of x bar. I will sum it 1 to n. Right, so this will become, because I am summing it 1 to n times, this will become 1 by n squared sigma squared, which is summed up from 1 to n. So I could clearly make out this is nothing but n times 1 by n squared times sigma squared, which will become sigma squared by n. So I could clearly see the variance associated with this sample is sigma squared by n, sample mean. So variance of the sample mean is sigma squared by n, mean of the sample mean or expected value of the sample mean is mu. And standard error, the other important term in this context, standard error of the mean, which is what we take as the standard deviation of the sample mean. Standard deviation, variance of the sample mean is sigma squared by n. The standard deviation of the sample mean is nothing but square root of sigma squared by n. So we could see that as n is increasing, right, sigma squared by n will be decreasing. So the standard error will be decreasing. So if the sample size is increasing, the standard error of the mean is coming down, which means the expected values of the sample mean is coming closer and closer to the population mean. So as the sample size is going higher and higher, the expected value of the sample mean is coming closer and closer to the population mean. So the deviance between the two is coming down quite drastically. And one more important point in the same context, the probability that x will take a value between mu minus c and mu plus c, going with the Chebyshev's inequality, if I want mean minus some standard deviation versus mean plus some standard deviation, it would come out as 1 minus sigma squared by nc squared. So that is the probability that x will take on a value between mu minus c and mu plus c. So important aspects for us to remember in this context. Then comes the definition regarding the central limit theorem, which is nothing but the limiting distribution of the standardized mean of n random variables. I am talking about the standardized mean of n random variables, and as n tends to infinity, as n becomes larger and larger, what is the distribution of the mean of the sample mean? The sample mean we have already seen earlier. The expected value of the sample mean is the population mean. Expected variance of the sample mean is nothing but the variance of the population divided by n. That's the same thing that is being brought out by the central limit theorem. If x1, x2, xn, they are a random sample. Population is having a mean of mu, variance of sigma squared. Moment generating function is mx of t. The limiting distribution, which we are calling as z, is x minus mu by sigma by root n. X is x bar here, which is nothing but the sample mean minus the, so here if you see this is the sample mean, population mean, and the variance, the standard deviation of the sampling distribution. Mean of the sampling distribution, standard deviation of the sampling distribution, and this is the mean of the population. So this is what we are, the limiting distribution z, the limiting distribution of this x bar, as n is larger and larger and larger, the x bar minus mu will become almost closer to 0, because x bar and mu approach quite closer to each other, and this is what we are calling as a standard normal distribution. So it justifies this concept, which is the central limit theorem. It justifies approximating the distribution of the sample mean with a normal distribution, having the mean and variance, the same thing above mean variance would be applicable when the sample size is greater than 30. When we are saying n is so large, from a practical application perspective, I am taking whenever n is greater than or equal to 30, I can very well apply the central limit theorem quite comfortably. Now, if I have to quickly look at the application of the central limit theorem, probably it's much more complicated, but let me just quickly try to get into this central limit theorem. So we know a few important points regarding the moment generating function. We have already discussed, so I want to use those things here. When I say the moment generating function of x, we already know mx of t. But let's say if I want to find the moment generating function of x plus a, which is nothing but the expected value of e to the power of x plus a into t, which works out as e to the power of at times mx of t. We have already looked at the results, but I'm quickly recollecting them. And we have also used the result earlier, m bx of t. If I am talking about moment generating function of bx, which is a multiplication of x, which is also nothing but the expected value of e to the power of bxt, I can very well write it as e to the power of, I can very well write it as bt, which becomes mx of bt. This is one more result. And at the same time, if I am trying to find out x plus a by b, the moment generating function associated to x plus a by b, I could very well combine these two things kind. So I can very well write it as e to the power of x plus a by b times t. So I could see that I can take out e to the power of a by b t outside, and it would still be 1 by bx. So I can very well write this as mx of t by b. So these are some of the results that we already know regarding the moment generating functions. When a constant is added, constant is multiplied, constant is added as well as divided. So using these things, I'll slowly go ahead with finding out mz of t, wherein z is nothing but we have right now defined it as x bar minus mu by sigma by root n. So I'll take this one instead of z. So going with this same rule here, I subtracted something, I divided it by something. So I'll get e to the power of a by bt. So e to the power of minus square root of n times mu t divided by sigma. So this is this part, and I am also taking mx bar of t by b. Here the b for me is nothing but 1 by sigma by square root of n. So which will become square root of nt by sigma. Right? So this part, and if I am still continuing this, it is nothing but e to the power of minus square root of n mu t by sigma, and m, if I very well take out 1 by, right, I'll typically make it out as if I'm multiplying by n, it is becoming nx bar. If I'm taking nx bar, it is nothing but again an n is coming out here, which will make square root of n here, removing the square root of n from here. So now I'm looking at nx bar, which is also, see, n into the mean, which is otherwise I can take it as x1 plus x2 plus so on up to xn. So I can very well write now mz of t is nothing but e to the power of minus square root of n mu t by sigma. Now this whole thing, if you see, mx t by sigma root n, this is for one of them. Now I am talking about each one being independent. So for each one, if I am taking it this as a mean, right, because I have taken it from x bar, I am changing it to x. So this becomes mx, because they are independent and identically distributed. I am taking the moment generating function of each one of them, the product of that, because we know that the moment generating function of sum of independent random variable is nothing but the product of the individual moment generating function. So that using that, I will convert this into t by sigma root n. This is for one of them, and because for n of them I have to take, I'll take it to the power n. So now the next step wise, let me take the logarithm of mz of t. When I take the logarithm, obviously this e is going off, which is nothing but minus square root of n mu t by sigma, and this is n times log mx of t by sigma root n. So this is this part. Now mx of t by sigma root n, I can expand it as a power series of t. Right, mx of t by sigma root n, I'll expand it as a power series. So I'll get log mz of t. This would be minus square root of n by sigma mu t plus n times log mx of t. So log mx of t, because it's nothing but expected value of e to the power of t. So this is where I am expanding it, which is nothing but the first moment multiplied by t by sigma root n, then the second moment mu 2 squared t squared by 2 sigma squared n. Similarly, you have mu 3 cube, mu 3, which is the third moment, t cube divided by sigma root n whole cube into 3 factorial, so on, which means it is last one become mu n, so which is the nth moment, t to the power of n factorial sigma root n to the power n. So that is what, so I can very well take it till the infinite series. So we are getting mu 1 dash, mu 2 dash, so that is how you are expanding your moment generating function. So I am expanding this moment generating function mx of t. Right, we have tried out earlier expanding mx of t, which is nothing but mu 1 bar, which is the first moment times t, the second moment times t squared by 2 factorial, the third moment times t cube by 3 factorial, and so on. The same logic I am applying here. So where mu1 dash, mu2 dash, mu3 dash are all the moments about the origin. So I got the first moment, second moment, third moment about the origin. Now if n is, now continuing this proof a little bit more, if n is very large, right, even log 1 plus x I can very well expand. So again I can use the same expansion, log 1 plus x also, x plus x squared by 2, x cubed by 3, so on, where the x part is the total piece that is there inside. Mu1 dash t by sigma root n, mu2 dash, because we had log, right? So this is where I can take log mx, that n times log, we had that value, n times log mx of t. So that is where I can take the expansion of that by going with n times mu1 dash t by sigma root n. So probably let me try it out. So here I'll get log mz of t is nothing but minus root n by sigma mu t, that part I'm keeping it as such, n times, now log mx of t was there. So that is where I'll start taking mu1 dash t by sigma root n plus mu2 dash t by sigma root n squared 1 by 2 factorial. Similarly, mu3 dash t by sigma root n cube 1 by 3 factorial, and so on. This is the first part, minus 1 by 2 times again the same piece being kept inside, right? The same piece has to be kept inside, saying squared, because minus x squared by 2. This is x. This is my x part. So x minus x squared by 2 plus x cubed by 3. The same piece cube. So on. Now I can very well do the collection of the powers of t. So this is one power of t, right? Log mz of t. Now I can say minus square root of n by sigma mu. That is one power of t. Here also I have one more power of t, which is nothing but square root of n, because this is going off, square root of n mu1 dash by sigma times t. So this is how I am collating the powers of t. Now I can take t squared comes here. So this is n is going up. So which would become mu2 dash by sigma squared and 2 sigma squared. Similarly here also I will get, because I am doing a squared here, right? So because this whole thing is becoming squared, I can very well take it as mu1 squared, mu1 dash squared by 2 sigma squared. So this part I will get it as t squared. I can do all that stuff. Now mu1 dash is the first moment about the origin, which is also mu. Mu2 dash is nothing but expected value of x squared. So which is nothing but the variance plus expected value of x whole squared. So I can very well get mu2 dash minus mu1 dash whole squared is same as sigma squared. So I can very well expand the stuff for getting my log mz of t. I can do this kind of an expansion. Ignore all the higher power coefficients. And finally, when I take n tending to infinite, log mz of t will work out to half t squared. So once I remove the log, it becomes e to the power of half t squared. and e to the power of half t squared as n tends to infinity is nothing but this is associated with my standard normal distribution. So we can very well say z equal to x bar minus mu by sigma by root n will tend towards a standard normal distribution. That is how we can take the proof associated with this. But more than the proof, understanding the concept is more and more important for us in this context. So look at an example, quick, simple one. A soft drink vending machine is set so that the amount of drink dispensed is a random variable with a mean of 200 ml and a standard deviation of 15 ml. Right? And that too, because this is a sample, I can take it as x bar, and the sigma of x bar is being set as 15 ml. What is the probability that the average mean amount dispensed in a random sample of size 36 is at least 204? So we know sigma is 15. So the standard deviation of the sample, if I want, it is nothing but sigma by square root of n, square root of 36, 15 by 6, which is 2.5 ml. Now, we know that the mu is 200 ml, sigma is 2.5 ml, and according to the central limit theorem, this distribution is approximately normal because the sample size is greater than 30. So I can very well take the distribution of z, which is nothing but, I want at least 204. So x bar minus mu divided by sigma by root n. So this is coming out to be 4 by 2.5, which is around 1.6. And I can very well find out, when I am saying probability of x should be greater than or equal to 204, I can very well say probability of, x bar should be greater than or equal to 214, x bar minus mu by sigma by root n should be greater than or equal to 204 minus 200 divided by 2.5. So this is nothing but z here. Probability of z should be greater than or equal to 1.6. I can very well check it out from the tables to find out what is the probability that my z is greater than 1.6. Right? So that's the way we can solve the problems using the central limit theorem. Wherever we are seeing n is so large and we are talking about the distribution of the sample mean, I can very well apply the central limit theorem to compute the probabilities. When the population we are sampling is normal, the distribution of the sample mean is a normal distribution. Okay. So the above rule, whatever we have said, n should be greater than 30. Right? If n is greater than 30, then we are talking about the sample distribution will be a kind of a normal distribution. But if the population itself is a normally distributed population and I am taking a sample out of it, right? I am taking a sample of any distribution, then I require the sample size should be at least 30 so that the sample distribution becomes a normal distribution. But if the population that we are using, we know that it is already a normal distribution, then whatever the sample that we are taking out of it, and I am looking at the mean of that sample distribution, that will always follow a normal distribution only. I don't need to have a size of 30 or more. Even if it is 15 also, the sample the mean of that sample distribution will follow a normal distribution only. So there is no need of a size n greater than 30 if the population from which we are pulling the sample is already a normal distribution. If the population from which we are pulling the sample is not a normal distribution, then if I am interested in the sampling distribution of the mean, I need a minimum sample size of 30 so that it follows a normal distribution, right? Standard normal distribution. Alright. Now that you have a understanding of the central limit theorem, we will look at a few other distributions in this session. I want to talk about three different distributions here. One being the chi-square distribution, then I'll talk about the t distribution, and I will also bring in the f distribution. So we'll talk about three different distributions here. So getting started with the chi-square. We have already seen earlier that chi-squared is derived from gamma distribution. Is a special form of gamma distribution where alpha equal to nu by 2 and beta equal to 2. That's the reason if you look at the regular gamma distribution, we had the density function as 1 by beta per alpha, gamma of alpha, gamma function, x to the power of alpha minus 1 e to the power of minus x minus x by beta. So this is what was the density function that was associated with a gamma distribution. Now the special case of gamma distribution is a chi-square distribution where alpha equal to nu by 2, beta equal to 2. That's the reason the probability density function for a chi-square distribution becomes 1 by beta is nothing but 2, alpha is nothing but nu by 2. Gamma of alpha is nothing but nu by 2. X to the power of alpha minus 1, nu by 2 minus 1, which is nothing but nu minus 2 by 2, e to the power of minus x by beta, which is 2. So that is what is the probability density function associated with a chi-square distribution. And if you remember, the mean and the variance of the gamma distribution, the mean is alpha beta and variance is alpha beta square. The same logic here, mean is nu by 2 times 2, which is nothing but nu. Variance is nu by 2 times beta squared, 2 squared, which is nothing but 2 nu. So that is where the chi-square distribution is having a mean of nu and 2 nu. Now the same logic, if I am going with the moment generating function, mx of t, it is nothing but 1 minus of beta t to the power minus alpha. So that is for a gamma distribution. So this I can very well say mx of t here, the moment generating function is nothing but 1 minus 2t whole to the power of minus nu by 2. So all these things, they can very well be derived from your gamma distribution once you know that gamma distribution is having a special case where nu equal to 2 and beta equal to where alpha equal to nu by 2 and beta equal to 2, it forms a chi-square distribution. On the other side, one more way to approach a chi-square distribution is if x is a standard normal distribution, right? So which is nothing but x minus mu by sigma is this is what we are calling as a standard normal distribution with a mean 0 and variance 1. Then x squared is having the chi-square distribution. This is one more relation. If x is following a standard normal distribution, then x squared will follow a chi-square distribution. That's one more important relationship that you need to remember. So that's the reason chi-square distribution is having a very important role when we are trying to do this sampling from the data which is having normal population. So wherever the data is more and more normal, and I am trying to do the sampling from that particular distribution. So if X is having a standard normal distribution, we can very well say that the X squared follows a chi-square distribution. So because X squared is nothing but we can use it to make inferences regarding the variances of the sample. Inferences regarding the variances of the sample can be made quite comfortably using the squares. So that's the reason chi-square distribution plays an important role when we are trying to make inferences regarding the sample variances. In the next couple of slides we would be seeing, if I want to make some kind of inferences regarding the sample mean, I'll be using the t distribution. But if I am making some kind of inferences regarding the sample variances, then one of the important distribution that I would rely on is the chi-square distribution itself. Some important properties associated with the chi-square distribution, right? If the X is a standard normal distribution, then X squared is having a chi-square distribution with nu equal to 1 degree of freedom. So if you look at the moment generating function, right? So if I am talking about a moment generating function in the earlier case, so with 1 degree of freedom, right? If X is a standard normal distribution, X squared as the chi-square distribution. So if you look at the moment generating function here for X squared, it is nothing but 1 minus 2t to the power minus half. So this is the distribution associated with the X squared part. Probably you can generalize it and we can look at it quickly. If x1, x2, xn are independent random variables having standard normal distribution, so each one is having the standard normal distribution, then the summation of their xi squares, the summation of their squares is having a chi-square distribution with n degrees of freedom. So in the earlier case we have also, this is the moment generating function we have got for one of them. Xi squared, I got it as 1 minus 2t to the power minus half, and now y is what I am saying, xi squared sigma xi squared, so the summation, which is nothing but, if I want the moment generating function of y, which is nothing but the moment generating function of the summation, because they are all independent, I can take it as the product of their individual moment generating functions, which will become 1 minus of 2t to the power minus half to the power n, which is 1 minus 2t to the power minus n by 2, which is what is becoming n degrees of freedom. So I can very well use that kind of a rule as well. But one thing you remember, X is a standard normal distribution. X square is having a chi-square distribution with 1 degree of freedom. Another important property or the result, x1, x2, xn, they are all independent random variables. Each one is a chi-square distribution, v1, v2, nu1, nu2, nu n degrees of freedom. Then their summation. So each one now is not following a normal distribution. Each one is a chi-square distribution already. So this one is having nu1 degrees of freedom, this is having a nu2 degrees of freedom, and so on. And now if I am doing the summation of all these things, that also will have a chi-square distribution, but the number of degrees of freedom will be sum of the degrees of freedom of all of them. So basically it's like, if x1 is a chi-square distribution with nu1 degrees of freedom, x2 is a chi-square with nu2 degrees of freedom, then it is simply said that x1 plus x2 is also a chi-square distribution, but with nu1 plus nu2 degrees of freedom. That's a simple application of this particular rule. Then the same logic can be extended, right, for any number of variables as well. Another important aspect regarding the chi-square, if x bar, which is the mean, sample mean, s squared, sample variance, so they have the mean and the variance of a random sample, size n from a normal population. The population is having a mean mu, and the variance of the population is sigma squared, which means the standard deviation of the population is sigma. A few important points for us to understand in this context: x bar is independent. Even so the sample mean and the sample variance, both of them are independent. But more important part that we really need to understand here is n minus 1 times s squared by sigma squared. N minus 1 times the sample variance divided by the population variance is having a chi-square distribution with n minus 1 degrees of freedom. So this is a very important part which we will be using in a lot of numericals out here, right? So this is, you always remember this part, saying n minus 1 s squared by sigma squared, where s squared is the sample variance and sigma squared is the population variance. The other way of writing it is s squared divided by sigma squared by n minus 1, which is nothing but this is the sample variance, this is the population variance divided by the degrees of freedom. So n minus 1. So this would be a chi-square distribution with n minus 1 degrees of freedom. So this result is heavily used in a lot of numericals. We can see this example that we have at the bottom to understand how I can use it. Integrals of this, so for chi-square distribution, the calculations are heavily tabulated. You will find alphas 99.5%, 99%, 97.5, 95, 5, 2.5, 1.5%. And for all kinds of new values, 1 to 30, right, which is nothing but these are the degrees of freedom that we are talking of here. And it comes out in such a way that the area to the right under the chi-square curve will work with that new degrees of freedom. So if you are typically looking at the sample table, this would be a table, this would be a chi-square distribution, right? So in this chi-square distribution, this would be the shaded region. So this shaded region is what is your alpha part. In some cases, if I am saying this is 0.005, so this shaded part is 0.5%. Or if we are saying it is 0.01, then the shaded part is 1%, and so on. So in some cases the shaded part could be 1%, shaded part could be 0.5%, or here it is 2.5%, 5%, or 95%, and so on. I am trying to find out what is the area under this chi-square curve, which is chi-square curve, the area under the curve towards the right of this particular alpha. So where the probability of x greater than the chi-squared value should be equal to this particular alpha number. That is what is the solution that we typically provide. Look at this numerical which can help us in solving that example. Suppose the thickness of a part used in a semiconductor is its critical dimension, and that the process of manufacturing this part is considered to be under control if the true variation among the thickness of the part is given by a standard deviation not greater than 0.6. So I want the true variation given by the standard deviation. So sigma squared, or sigma is 0.6. So sigma squared will be 0.6 squared which is 0.36. To keep a check on the process, random samples of size n equal to 20 are periodically taken, and it is regarded to be out of control if the probability that the S squared will take on a value greater than or equal to the observed sample value. So the actual value greater than or equal to observed sample value is 0.01 or less. What can you conclude about the process if the standard deviation of such a periodic sample is 0.84? So for one of them, we got, when we have taken a size of 20, we got the standard deviation of the sample as 0.84. Now we can very well find out. So we can take it as out of control when you find n minus 1 times s squared by sigma squared. It is exceeding the chi-squared value. The chi-squared associated with what is my alpha here, 0.01, and I am taking 19 degrees of freedom. So I have to find out this alpha chi-squared value with new degrees of freedom and with alpha as 0.01. So let me try computing that value using my Excel. First of all, I need the chi-squared value. So if I try to find out, I can look at the chi-squared tables as well. Right, the chi-squared distribution I am taking. The x is, no, I want chi inverse. From the value I want, the probability is 0.01, degrees of freedom is 19. So, sorry, this is comma. So this comes out as 7.63. So this is the chi-squared value as per the table. So if I see that my n minus 1 times s squared by sigma squared is greater than the chi-squared value associated with this 19 degrees of freedom. Right, if I get my chi-squared value, okay, in Excel I have to compute it from the left always. Right, I want the area 1% towards the right. This is the 1% area towards the right, right? So I have to compute it as 99% because I'll always, in Excel when I am computing, I'll take it right from the left. But when I am referring to the table, I can directly refer to the area under the right side, which is 0.01 itself. So in this case, my table value is coming out to be 36.19. Now I'll compute my n minus 1 s squared by sigma squared. N minus 1 is 19. S squared is 0.84 divided by sigma square, S is 0.84. So S squared is 0.84 squared. Sigma squared is 0.6 squared, making it 37.24. So 37.24 is greater than 36.19. So this rule is getting met. N minus 1 s squared by sigma squared is greater than the chi-squared with 1 degree of significance level of 1% and 19 degrees of freedom. So based on this, I am able to say that the process is going out of control and I have to have an improvement to the process. But of course, this whole conclusion I can very well make if I am saying, nowhere it is mentioned, but if I am considering that the data that I am picking is a sample from a normally distributed population itself. Because my sample size is very small, I have to really make an assumption that the sample is more or less normally distributed in this case. So that is how I can understand the chi-square distribution, solve the numericals associated with the chi-square distribution. Alright. Now, moving on to the next distribution, which is the T distribution, or otherwise called as the student T distribution. Here, couple of important points. So this is also talking about samples from the normal population having a mean mu, variance sigma squared. Here we talk about X bar is having a normal distribution with mean mu, sample mean. We already know this, right? If the population is having a normal distribution with a mean mu and a variance sigma squared, the sample mean is having a normal distribution with a mean mu and a variance sigma squared by n. But here the problem comes, what is the value of sigma? Most of the real world problems, I don't know what is sigma squared. What is sigma? I don't know the standard deviation of the population. So which means I have to replace the standard deviation of the population with the standard deviation of the sample. So when I am replacing the standard deviation of the population with the sample, then my sample distribution does not become a population, does not become a normal distribution. Right? If I know that my population is a normal distribution with a mean mu and a variance sigma squared, then my sample mean is following a normal distribution with a mean mu and variance sigma squared by n. But if I don't know the variance of the population and I have to replace it with the sample variance and the sample standard deviation itself, this is where my sample mean cannot follow a normal distribution because I don't know the variance of the population and I am estimating it with the variance of the sample. Now this is where the X bar cannot follow a normal distribution. Here we have a slightly different kind of a distribution coming into picture. That is what is the T distribution. Because the S itself is a distribution. We have seen that the S and sigma can be linked through the chi-square distribution. We said n minus 1 S squared divided by sigma squared follows a chi-square distribution with n minus 1 degrees of freedom. So I can very well apply that concept here, right? So now looking at how the T distribution is coming into picture, let's talk about two random variables wherein y is having a chi-square distribution with new degrees of freedom, right? It's a chi-square distribution with a new degrees of freedom, and z is having a standard normal distribution. Then I'm talking about z divided by square root of y by nu. Square root of y by nu. Nu is nothing but degrees of freedom, because if you remember, when we say z, this z is a normal distribution, and if you look at y, I am calling it a chi-square distribution with if you see here, n minus 1 S squared divided by sigma squared follows a chi-square distribution, right, with n minus 1 degrees of freedom. So when I am doing chi-squared divided by n minus 1, it's nothing but S squared by sigma squared, and if you are putting a square root under it, it is nothing but S by sigma. So if I am trying to put if I am trying to find out the z divided by square of y by nu, I am taking the density function of that as gamma of nu plus 1 divided by square root of sigma nu gamma of nu by 2 1 plus t squared by nu to the power minus nu plus 1 by 2. So this is what we call as the t distribution. This is the typical PDF associated with the t distribution, and this is having nu degrees of freedom. Now, a simple way to arrive at this as well. I mean, when you are trying to remember it, it becomes very complicated. But if you try to look at y and z, I have said y is nothing but it's a chi-square distribution with n minus 1 degrees of freedom or nu degrees of freedom. Right? I said chi-squared with a nu degrees of freedom. And z is a standard normal distribution, means 0 as the mean and 1 is the variance. I can very well take the joint PDF, which is nothing but f of x comma y or f of y comma z here. I'll take f of y comma z. Z is a normal distribution, so the probability density function of a standard normal distribution 1 by square root of 2 pi e to the power of minus half z square, and at the same time, because they are independent, their joint probability density function is the product of their individual PDFs. And now y is a chi-square distribution. So for a chi-square distribution, we have already got 1 by beta to the power alpha. Alpha here is nu by 2 for a chi-square distribution, which is having nu degrees of freedom. Then I have gamma of nu by 2, x to the power of alpha minus 1, nu by 2 minus 1, e to the power of minus x by beta, which is nothing but minus y by beta is 2. So this is what will come out as the joint PDF. Here y is greater than 0, right, because y is a gamma distribution, whereas z lies between minus infinity to plus infinity because it's a standard normal distribution. And everywhere else the f of yz is 0. Then here we will go with the change of variable technique, which we have used in our earlier session. I'll use a change of variable technique wherein which is a transformation I am performing to solve. Now we have t is nothing but z by square root of y by v, right? Y by nu. So we have t is nothing but z by square root of nu by v. So from here I can very well get z is nothing but t into square root of y by nu. So I'm trying to find the inverse function, right? So first I'm trying to solve it for z. I'll try to replace z. So which means z should be expressed in terms of the other two, right? Initially I'll try to find y comma t. I'll try to take out z. So that's where I'm taking the inverse of it. So for that I should be able to find the value of z in terms of other two, and at the same time the derivative of the z also with respect to t I should be able to find it out, which is nothing but square root of y by nu. If I have that, now I can find the joint density function with respect to y and t by taking out the z, which is nothing but f of y comma t. So I will wherever I had z, I'll replace it with this relation and I'll multiply it with dz by dt. So this is where I'll start. So the gamma part, the new part, which is the y part, I'll keep it as it is. So it would be 1 by 2 to the power of nu by 2, right? And I have gamma nu by 2, this part will remain the same, x to the power of nu by 2. So now x, or here in this place of x I have tried y, sorry, y to the power of nu by 2 minus 1 e to the power of minus y by 2. So this part is the first part, but now this part is very crucial. 1 by root 2 pi e to the power of minus half, instead of z square I'll write it as t squared y by nu, because z is nothing but t into square root of y by nu. So z square I'll write it as t squared y by nu, and I have to also put the derivative of this, which is square root of y by nu. So this is what will become my g of y comma t. So if I am simplifying the g of y comma t, which is nothing but now 1 by the square root of 2 pi nu, right? I am taking out this as well as this, 2 pi nu. Then I have 2 to the power of nu by 2, gamma of nu by 2. Then I'll take y to the power of nu by 2 minus 1, e to the power of minus y by 2 times, this is 1, and I have t squared by nu. So this is the one I have with g to the power g of y comma t. Now the other thing is, I have to take out y as well, which means I am doing an integration across all the y. Right? I'll do an integration across the whole y, and in this process I am substituting y equal to w equal to y by 2 into 1 plus t squared by nu. This whole thing I'll substitute some w. Right, when I am substituting this whole thing as some w and doing an integration, so this will become, now you look at the integration of this whole thing. So by substituting this will become y is nothing but 2w by 1 plus t squared by v, right? And this is dy. dy is nothing but dw, right? So we are getting dw as 1 by 2 times 1 plus t squared by nu dy. So dy also becomes 1 by 2 dw by 1 plus t squared by nu. This will become my dy as well. Now you could very well write out all these things, which is nothing but 1 by root 2 pi nu, 2 to the power of nu by 2 gamma of nu by 2, y to the power of nu by 2 minus 1, y is nothing but 2w by 1 plus t squared by nu. So this 2w also I can very well write it as nu by 2 minus 1. Even 1 plus t squared by w I can write it as nu by 2 minus 1. And e to the power of minus, because it's y by 2 the whole thing, I'll write it as w. And dy I can very well write it as 2 dw by 1 plus t squared by nu. So this is becoming the whole stuff. Now you can do a quick rearranging of the terms. First time, if you see here, there is e to the power of minus w, right? Here there is e to the power of minus w and w to the power of this, the nu by 2 minus 1. So I can very well write it as nu by 2 plus 1 minus 1, alpha minus 1. So my alpha is becoming nu plus 1 by 2. So I can very well write this after simplification. This would become gamma of nu by 2 plus nu plus 1 by 2, gamma of nu plus 1 by 2 divided by square root of pi nu gamma of nu by 2. So you'll get this 2 to the power of nu by 2 going off here, because we are getting 2 to the power of nu by 2 here. 2 to the power of nu by 2 minus 1 is this one, and you have another 2 here. So overall it is becoming 2 to the power of nu by 2. This is getting going against this. So this integral is coming out to be 1 internally, and I have this part in the numeric in the denominator part. So I'll take it as to the power nu by 2 minus 1, and here I have 1. So overall it is becoming nu by nu plus 1 by 2. I take it to the numerator, making it nu minus minus of nu plus 1 by 2. So overall it is coming out to be the density function that is associated with the t distribution. So you can very well simplify this whole thing by changing. So this kind of a simplification is typically possible by doing a change of variable or a transformation kind of an example. So you can very well use the transformation. First take out your z and then try substituting for y. You will get the PDF associated with the t distribution. And again, you don't need to be worried so much regarding the values associated with the t distribution. Right, the PDF associated with the t distribution looks very complicated, but there are so many there are large number of values that are tabulated for different values of alpha, 10%, 5%, 2.5%, 1% for all different values of alpha, and for different degrees of freedom they are extensively tabulated. So we can very well refer to the t values from the data itself. And graphs of the t distribution having a different number of degrees of freedom. So you could see that this is the graph of a t distribution which is having 2 degrees of freedom. This is the graph of a t distribution having 10 degrees of freedom. And as you see here, as the number of degrees of freedom is increasing, and the final one is a graph of a standard normal distribution. So as we see that the number of degrees of the freedom is typically increasing, the graph of a t distribution is very much approaching a normal distribution, a standard normal distribution. So that's one more important relationship that you need to be comfortable with when you are working with the t distribution. So especially when you have a population whose variance is not known. Now let's generalize this part. I'm talking about a population whose variance is not known. I'm taking a sample from this particular population. So when I'm taking a sample from this population, if I want to know the distribution of my sample mean, it will follow only a t distribution with n minus 1 degrees of freedom. N minus 1 where n is my sample size. So it will follow a t distribution with n minus 1 degrees of freedom. But as the degrees of freedom for a t distribution is increasing, we have seen that the t distribution will approach the normal distribution. So if the sample size is much larger, even though the sigma variance of the population is not known, people try to approximate the t distribution to a normal distribution. So because of that reason, the normal distribution standard normal distribution can very well be used as a substitute for t distribution when the sample size is large, even though the population variance is not known. So that is what it is. If x bar and s squared are the mean and the variance of the sample size n, normal population having a mean mu and variance sigma squared, then the t, which is nothing but x bar minus mu by s by root n, is following a t distribution with n minus 1 degrees of freedom. We can take up a numerical in a 16 1-hour test runs. So the sample size is 16. The gasoline consumption of an engine averaged 16.4 gallon. So the x bar, I've got it as 16.4. Standard deviation of 2.1. So this is for a sample. The sample standard deviation is 2.1. Test the claim that the average gasoline consumption of this engine is 12 gallons per hour. So I have to check whether it is mu equal to 12 or not. So now I have all the data. So we can use it into the t distribution because I don't know the population variance here. I am using the sample variance as a substitute for the population variance. So the t for me is nothing but x bar 16.4 minus mu, which is 12, s by root n, which is 2.1 by square root of 16, which is 4, which becomes 8.38. One simplification, I am getting 8.38. Right, we can very well look at it in our spreadsheet. So I am getting x bar 16.4 minus 12 divided by 2.1 by 4, 8.38. Now here the number of degrees of freedom is n minus 1, 16 minus 1, 15. So I need to find the typical value associated with the t distribution with 15 degrees of freedom. So I'll find t inverse. Then what is the I'm talking about what is the level of significance here? Let's say I want I want 1.01 being the level of significance. I can very well take it with respect to 0.99, and I can compute the value for 15 degrees of freedom. The table value is working out to 0.012. Even if I'm talking about 0.01 here, the area under the curve, because I want the value to be greater than. So this is 2.94, right? 2.94 corresponding to 0.01 area from the left, but my actual value is 8.38, which is greater, and because of that particular reason, I can very well conclude that the true average consumption in this case is very much higher than 12 gallon. The claim is 12 gallon. We'll talk more and more detail about it when we are doing a testing of hypothesis. But how to use the t distribution and the t table computation is what is primarily being looked at here, right? So this is what should give you a basic understanding regarding the t distribution and the application of the t distribution in various numericals. Especially when the population variance is not known and I am trying to find the distribution of the sample mean, I cannot say that it will follow a standard normal distribution. It will definitely follow a t distribution with n minus 1 degrees of freedom. But as the number of degrees of freedom increases, goes larger, we have seen that the graph of the t distribution more or less goes closer to the graph of the standard normal distribution. That is where I can make an assumption, or I can make an assumption that the t distribution is more or less similar to the standard normal distribution. I can approximate both of them only when the sample size is much larger. But otherwise, when the population variance is not known, I will say that the sample mean will follow only a t distribution with n minus 1 degrees of freedom. Alright. Now, One more topic that we are looking at in this context is the F distribution. This is also something that is very much useful when you are doing a sampling from normal population. So this is primarily focusing on two independent random variables, x1 and x2. And both of them are having separate chi-square distribution. So this is the first one is having a chi-square distribution. Probably you look at this statement first. U is having a chi-square distribution with nu 1 degrees of freedom. V is having a chi-square distribution with nu 2 degrees of freedom. Then we can say F is U by nu 1 divided by V by nu 2, which is nothing but the distribution divided by the respective degrees of freedom. So I'm more interested in the distribution of this, right? The independent chi-square distribution divided by its degrees of freedom, chi-square distribution 2 divided by its degrees of freedom, and that is what I'm calling as F. Now the sampling distribution associated with this particular F is what we are calling as an F distribution. Right, the chi-square is two independent random variables having their own chi-square distributions with different degrees of freedom. The ratio of those two is what we are calling as a F distribution. So that's the reason for any kind of inferences regarding the ratios of two sample variances will generally use the F distribution. So F distribution has a lot of applications. In analysis of variance, we'll use the F distribution. In regression, again while performing analysis of variance, we are doing an F distribution. So there are so many applications of F distribution in the real world. And just like a T and chi-square, for different values of alpha, for different combinations of nu 1 and nu 2, we see the values that are associated with the F distribution. So which is equivalent to the probability that the F value is greater than that particular level of significance, degrees of freedom for the first one, degrees of freedom for the second random variable. So the probability that this is greater than or equal to this is the alpha, which is the area under the curve. And this is the PDF that is typically associated with the F distribution. Now what I suggest is you can very well work it out. Again, these are two different chi-square distributions. Just to give a quick hint here, there are two different chi-square distributions, U and V. So I can very well take the first one, the PDF of the first one, which is nothing but 2 to the power of nu 1 by 2, gamma of nu 1 by 2, right, e to the power of minus nu by 2, nu 1 by 2, sorry, e to the power of minus y by beta, right? So I'll call it as minus u by 2, and I have u to the power of alpha minus 1. Alpha is nu 1 by 2 minus 1. This is the first one. Then because it is independent, I can multiply the probability density functions of both of them. 2 to the power of nu 2 by 2, gamma of nu 2 by 2. Then I have e to the power of minus u by minus v by 2, v to the power of nu 2 by 2 minus 1. So this is what is becoming the joint probability density function. So there are some of the things that can be equated. 2 to the power of nu 1 by 2 plus nu 2 by 2, gamma of nu 1 by 2, gamma of nu 2 by 2. Then u to the power of nu 1 by 2 minus 1 into u to the v to the power of nu 2 by 2 minus 1 into e to the power of minus of u plus v by 2. Then again I can use the change of variable technique, wherein I can say f is nothing but u by nu 1 by v by nu 2, right? So from here I can very well first get u, which is nothing but u by nu 1 is this one, so it becomes v by nu 2 times f times nu 1. So this is what is becoming this is what is becoming u. So I can very well change the variable. So and if I want to see do new by do u by do new do new by do f, I'm substituting it with f, right? So do new by do f, I can very well compute. It is v by nu 2 times nu 1. That is the do u by do f. So I can first find out g of f comma nu or f comma v. I can find out g of f comma v by substituting wherever u is there. I'll substitute with this and I'll take a derivative of this, and that is what will become my g of f comma v. After that I'll do an integration out for the whole of v, and based on that I can very well derive just like exactly the same derivation associated with the t distribution PDF. I can very well derive the PDF associated with the f distribution in the same manner. So you could see now change of variable technique will really help us in doing the simplifications more and more effectively. So whenever I am trying to do the comparison of the variances of two normal populations, saying is sigma 1 squared equal to sigma 2 squared. In that case, we are using f distribution quite effectively. So f is nothing but s1 squared divided by sigma 1 squared, s2 squared divided by sigma 2 squared. That's a random variable having an f distribution with n1 minus 1, n2 minus 1 degrees of freedom. So that is what is an application that is associated with the f distribution. We are trying to compare the variances of two different samples which are being pulled out from normal distribution. That's the reason f distribution is also called as the variance ratio distribution. Alright. So you should be comfortable with the applications of the chi-square distribution, the t distribution, as well as the f distribution. So that is what I have to talk about in this session. We looked at more important aspects relating to the sampling distribution of the mean, talked about the central limit theorem, then individually three different distributions associated with the sampling distribution, where we looked at the chi-square distribution, the t distribution, as well as the f distribution. If you have any further queries regarding the same, you can very well get back to me by giving me a call on the number that I have given below, or you can even send in an email at vamsidhar@facegurus.com. Thanks a lot for listening to this session. Thank you very much.